So today we're going to be talking about Netafim dripper quality, specifically two aspects, and this is engineering features that it's geared up for farmers. I know there's a couple of engineers who are watching, but this is actually for farmers. Now, what we're going to start off now is we're going to look at two criteria. The basic requirement of a dripper. A farmer, you the farmer, and your crop, you need a drip supply of water into the wetted bulb-shaped root zone on demand during the lifespan of your crop. Every dripper must be dripping the same flow rate. You want even water application throughout the field or the orchard, and you want therefore from that even fertilizer application. And this drip supply must never vary nor decrease over time. It must be accurate and constant over your crop's lifespan. By the lifespan, we've done it into three terms. You've got seasonal term, 1 to 2, 3 growing seasons, such as vegetables. Medium term, 4 to 10 growing seasons, such as sugarcane. And long term, that's your orchards. A good quality dripper. Now, a dripper is a dripper is a dripper. Not really. There is a significant difference between drippers. A good quality dripper can be defined as one that admits a predetermined flow rate that is accurate and constant over its intended lifespan. And to do this, essentially, the dripper needs to be kept clean. Keeping clean involves two aspects: the turbulence coefficient and your effective filtration area. And those are the two aspects that we're going to look at today. Now, just as a car tire has pressure using air, so too do drip lines using water. And where your tire pressure you normally put in is about 2 bars, the drip line pressure is normally about half of that, about 1 bar. A dripper has a flow rate, normally 1 to 2 liters an hour. And there's an inlet pressure inside that I've just mentioned just now, that's your 1 bar. Sometimes it can go above that in certain drippers that we call pressure compensating drippers. But for the purposes what we're going to be talking about here, we're going to stick it at 1 bar. And then you've got your outlet pressure, 0 bars. Now a dripper needs to reduce its inlet pressure from this 1 bar to 0 bar and still get 1 liter an hour through it. So something happens between the inlet pressure and the outlet pressure. An easy way would be to simply make a hole in the pipe. Now, to get 1 liter an hour, what you need to do is you'd have to put a hole that's about 0.17 millimeters in diameter, just under 0.2 millimeters. This is just a pinprick. 0.17 millimeters is the common strand of a width of human hair. And this produces a jet, not drip, and being so small, it can easily get clogged. Now, another way to create this friction loss would be to put it through a small pipe. Now, as water travels down a pipe, as I show here, it loses pressure. So we can see here, we've got starting off with 1 bar pressure, and as it travels down that pipe, in this specific example, it goes down to half a bar pressure. So as water travels down a pipe, it loses pressure. As it travels down a body, okay, if on your farm you throw some sticks or leaves into a canal or a stream, you will notice that the leaves or twigs that have landed in the middle of the stream flow downstream faster than the ones on the edges. Okay, that's friction loss. The body in which that water is contained creates a drag. So as water comes down a pipe, it loses pressure, and the longer the pipe, the more the pressure is lost. So in this diagram that I've got just shown here, if we have, in this case, a 100-meter long pipe and we lost that certain amount of pressure, in this case, from 1 bar down to 3/4 of a bar, and then if we double the length, we're going to double the friction loss. You can see here from 1 bar down to half a bar. This is exactly what the first drippers did. The first drippers that were done in the early 60s, they were just a long tube that create the friction loss. So being long like that, you took a long tube and just wrapped it around the dripper line itself. And this became formalized into a molded dripper. And in 1966, Netafim made the world's first dripper. It was a cylindrical dripper, but it had laminar flow. And this was a drawback. And I'll just now explain how that drawback occurs. Laminar flow. Laminar flow, if we talk about a canal, we see water flowing just gracefully down that canal. That's laminar flow, nice and steady. Conversely, if we look at the image on the right-hand side, there you can see a raging torrent. Now that's the opposite. That is turbulent flow. So if I was going to draw an analogy in keeping clean, if we take the laminar flow, you put your washing in a basin, leave it to soak overnight. That is akin to the laminar flow. However, the raging torrent, that is your turbulent flow. That is akin to putting your washing in a washing machine. So, in order to create that with the dripper, what we do is we put in, you can see the dripper in the left-hand side, there's your laminar flow. We put teeth into it. We put teeth and we create what's called a labyrinth. And that labyrinth then creates the turbulent flow. So what we have is here, you've got your laminar flow, akin to washing, soaking it overnight, and here we've got the washing machine effect inside the dripper with the teeth. And this, what it does, this turbulent flow keeps all particles that enter through this flow path here, and it keeps them in suspension, stops them getting deposited and encased along the edges of that flow path, okay, and out they come, keeps them in suspension the whole time, in and out of the dripper. And this dripper became formalized in 1970. That's what the first dripper looked like. It was a barrel shape. Nowadays, a modern dripper looks more like this. Okay, it's what we call a boat-shaped dripper, and that we weld onto the inside of your dripper pipe, such as you see in the top left here. So this washing machine effect is measured by the turbulence coefficient. The turbulence coefficient, it's a measure, it's a number that we use to measure the effectiveness of this washing machine effect. The turbulence coefficient, there's a formula on the left-hand side of the screen. I'm not going to delve into that. It's just to show you that it does come from somewhere, from general hydraulic theory. But what I just want to emphasize and make the point is that it is a value. We call it K. And the greater the value of K, the better the dripper is at keeping clean. Now that turbulence coefficient depends on three primary things within that labyrinth. The labyrinth width and depth, the length of the labyrinth, or in the case where we have teeth in it, the longer it will be, the more teeth it will have, so there'll be the number of teeth. And then the design of the labyrinth itself. I'm going to show you those three aspects now. The depth and width of the labyrinth. The greater the depth and the width, the better. The greater these dimensions, the greater the turbulence coefficient. Okay, the greater we've got the width here, and the greater the depth, the better will be the turbulence coefficient. More means more. On the other hand, the length of the labyrinth, the shorter is the better. So that will mean the shorter we've got, the less number of teeth. So the shorter the flow path, the greater the turbulence. So in this case, less means more. Now, just now I said we're going to put in turbulence, we're going to put teeth in to create the turbulence. So you might think, well, okay, well, then therefore the teeth create the turbulence. So the more teeth, the better. The less teeth you've got, the more efficient is each individual teeth at creating this pressure loss that I mentioned that goes from 1 bar to 0 bar. Now, if we look at this design now, this is the third thing that I spoke about, the design and manufacture of the labyrinth. From the left-hand side of the screen there, you can see a labyrinth that has got rounded edges to it. And then as we move right, we've got mesh teeth, align teeth, turbonet gap, the turbonet. Now, what this is the turbulence coefficient is going from not so good where the rounded teeth are, going right to the right-hand side of the diagram, and there you've got the best. Rounded edges create less turbulence than razor-sharp edges. What we've got, if you could imagine, where I'm pointing to now in a mold that's creating a dripper, you've got molten plastic flowing down where I'm pointing to now. And as it's flowing down, it has to displace air, it has to expel air. And if you don't get that manufacturing process exactly correct, you're going to end up with a little bit of air left in the end if you can't get rid of that air. So if you're going to end up with air there, you're not going to get the rounded razor-sharp edge that you want. Okay? So that's one thing that can create these rounded edges. Another is when we take that dripper, we weld it onto a pipe. So if you weld anything to anything, you're going to get distortion. Okay, so that's the second thing that can create the welded. The rounded edges. Then we've got a bit of a better labyrinth here, where I'm pointing to now. There you can see the teeth are kind of like interlocked, they mesh. Okay, so rather than turbulence, what that is just kind of creating a wiggly waggly flow path. Then if we break those teeth apart a bit, now you can see where it just got this broken line here. Now you can see we're getting away from that wiggly waggly flow path, and now we're getting a bit more turbulence there which we can create. And then if we break it apart even more, we're going one step up, and that's what we call, in Netafim, we call the turbo net gap. And then finally, where we take those teeth, this is the next generation, we torque them a little bit, okay? And we have the Turbinex, and that gives even better turbulence. I'm going to delve a little bit into the actual design here. If the design and manufacture of the labyrinth is not optimal, the less turbulence is created, and the more the dripper will need to resort to friction loss to achieve that 1 bar pressure loss that is required. Now, in the images below, you can see a yellow dripper. This is a copy of a Netafim dripper on the left. The black one on the left is a Netafim dripper. Now, with the yellow one, the required 1 bar pressure loss has not been achieved with this labyrinthine design. And what it has had to do is had to resort, therefore, to make up that pressure loss with more friction loss. So it's had to make the labyrinth longer. So you can see here with the Netafim black dripper, that red area is the inlet to the dripper. And then our flow path goes down here. With this one, you cannot achieve the 1 bar head loss. So what they've had to do is they've had to make this longer. This results in double punishment, as not only is the labyrinth longer, but in order to make it longer, what they've had to do is they've had to encroach on the inlet of the dripper and make that smaller. Now what that does is make the filtration area smaller, and that's what we're going to look at now. So we say, as I've said just now, you need razor-sharp teeth. Razor-sharp teeth create high turbulence. The higher the turbulence, the less teeth you need. Less teeth, the shorter the labyrinth, and the larger your filter can be. So this is a Netafim dripper with a bigger diagram. You can see here, there's the inlet. Now it flows down that flow path and out of the dripper. Now this one here, you can see this close-up here, these teeth are not as rounded as those ones here. They're rounded teeth, so you've got lower turbulence. So therefore they've had to add in more teeth. And therefore, you've got a longer labyrinth and a smaller filter. If you cannot achieve these razor-sharp teeth, you have no option other than to increase the number of teeth or narrow the labyrinth or both. Now we look at the filtration area. We just seen just now that if it's too small, that's not what we want. Now let's look at the layers of filtration on an irrigation system itself. Pre-filtration. This is filtration before we get into the irrigation system. Easily dirt and contaminants, because it's before we get into the irrigation system, they can be got rid of before we get into the irrigation system. And then we have primary filtration. Primary filtration, these are the filters that you see on an irrigation system, the visible part of an irrigation system. And these we backflush, and in the backflushing process, dirt is removed from the irrigation system. And then thirdly, what we call secondary filtration, these are where we put the filters in the field itself. Sometimes they're backflushed automatically, and sometimes we clean them by hand. But regardless, dirt is nevertheless removed from the system. Now the last line of filtration, the dripper itself. neither back flushing nor cleaning by hand are possible. So there we've got the actual filter is actually at the dripper itself. Now at this last line of filtration, the dripper itself, dirt removal from the outside of the dripper can be achieved by flushing dripper lines. However, much of the dirt that is trapped by the dripper filter may never be removed, despite adequate dripper line flushing. A dripper with a smaller filter area will become covered up and used up before a dripper with a larger filter area. So the longer a dripper needs to last, the larger that dripper area must be. I'm just having a look at the longevity of a dripper. I've just brought in a note here about longevity of a dripper line, but the emphasis here I'm talking about is the longevity of the actual dripper itself. In a dripper line, we've got wall thicknesses. The heavier the wall thickness, the longer the dripper line will last. And in the same vein, dripper line longevity, the bigger the dripper, the longer the dripper will last. So what we do is bigger drippers tend to go, the bigger dripper is going to last longer, will go into a dripper line wall thickness that will last longer. And likewise, smaller drippers, which are not designed to last as long, they will go into smaller wall thicknesses. The wall thicknesses, just basically, we put into 3 categories: thin wall, medium wall, and heavy wall. And as I mentioned at the beginning of this webinar, that would be used, your thin wall, for your 1 to 3 growing seasons, your medium wall from 4 to 9 growing seasons, and the heavy wall from 10 growing seasons or more. That's your orchards. Modern Netafim drippers areas cover almost the whole underside of the dripper. I've got 3 drippers here, Netafim drippers here. The top left here, this is Uniram. That's our top of the range dripper. And then we have that pressure compensating dripper. Then we have a non-pressure compensating dripper, which we call Aries. It's also a big dripper. And you can see again, your dripper area, that's these veins here. They cover almost the underside of the dripper. Then we've got a slightly smaller dripper here, the DripNet PC. That's the same as Uniram, as a pressure compensating one, just a little bit smaller. But you can see again, the dripper area covers the whole of the underside of the dripper. You can see here, this is a Uniram dripper. This dripper here, you can see over time has come covered up with slime. You can see here, this is a dripper line that's been cut into and opened up, and then this thing here, that's a Uniram dripper. This dripper, despite being covered up with the slime, is actually you can see that hole there, that hole there, and that hole there. This dripper is still dripping. Okay, so and it takes time for this to get blocked up. So the larger that dripper is, the longer it will take before this sort of thing happens. Turbulence coefficients. Numerically, turbulence coefficients range from the low end to the high end 1 to a high value of 10, sometimes more than 10. And filtration areas tend to be at the lower end 10 square millimeters up to 100 square millimeters or even more. Those are the ranges that we use, the numerical values of these two. Now, if we look at Netafim drippers, as you just mentioned a couple of slides ago, Netafim Uniram, that's our top of the range dripper. I'm looking at 1 litre an hour drippers for all of our drippers. That's got a turbulence coefficient, the Uniram, of 10.4. And a very, very big filtration area, 130 square millimeters. We then drop down. If I go to Aries, as I mentioned, this is the non-pressure compensating dripper, and there we've got a filtration area of 49. And then DripNet PC, that was that slightly smaller pressure compensating. That's what PC actually means, is pressure compensating. And that's got 42 square millimeters. Now the DripNet PC, you can see, it's got a very high turbulence coefficient. And then we've got the turbulence coefficients of our non-pressure compensating drippers, the Aries, Typhoon Plus, and the Streamline X. Now, if we look at other values, our competitors, typical values that you would get on the lower range of the turbulence coefficient would be about 2.4 to 9.4. I haven't seen a dripper yet with a turbulence coefficient higher than 9.4. And then the filtration area can be right the way down at 1 square millimeter up to the highest that I've seen is 47 square millimeters. So When you're assessing dripper quality, and you're looking at two drippers, you have to ask the questions: what is its turbulence coefficient, and what is the effective filtration areas of the drippers when making your choice? Now, the impact of the turbulence coefficient on you, the farmer. A farmer and your crop, you don't care about the specifics and technical details of the dripper. Your only concern is what the dripper delivers. You need a drip supply of water and fertilizer into the root zone on demand during the lifespan of your crop. This drip supply may never vary nor decrease over time, and it must be accurate and constant over the crop's lifespan. Essentially, your dripper must be kept clean, and on this you depend on turbulence. In the filtration area, simply, the larger the area of the filter's dripper, the more area on which to accumulate contaminants, and the longer it will take for the area to get covered with those contaminants. So essentially, the larger the dripper, the longer it will last. So in summary, to keep a dripper clean, we need the washing machine effect. This is the turbulence. Turbulence is measured by the turbulence coefficient, which we call K. And the greater the K, the greater the value of K, the cleaner the dripper. And that turbulence coefficient, K, depends on the labyrinth depth, width, and length, the number of teeth, the design and manufacture of the labyrinth, including the teeth, and the effective filtration area. The greater, the better, and the longer it will take to block. Why Netafim? We understand your priority, a sustainable and efficient irrigation system. We want to give you the farmer, we want to give you the tools to make the correct decisions and overcome your challenges. And our team in the field is equipped to support our dealer network in helping you, the farmer, apply our quality products with the right knowledge for an optimal return on investments. Take on precision irrigation with the right team by your side. I'm now going to close with and ask if there are any questions that you may have.
Thank you very much, Jerry. We did receive a couple of questions. The first question is, do drippers get less efficient as they get older?
Okay. As I mentioned, if you can keep it clean, then the turbulence coefficient will remain the same. And if the turbulence coefficient remains the same and the filtration area lasts the lifetime, then it will remain the same. Its efficiency will remain the same. This is the whole object, as I mentioned from the beginning, is keeping that constant flow rate from day one to whatever the last day of your crop is. So if you follow these guidelines that I've just mentioned, no, there's no reason that your efficiency should decrease. That's what the whole object of this webinar has been, is to maintain that efficiency, maintain that flow rate throughout the life of the crop.
Thank you, Jerry. Next question is, how do the quality of welding influence the dripper quality?
Okay, so in our factories throughout the world, we take those drippers and we weld them to the inside of the wall of the pipe. If the welding is not optimal, now this is an engineering process, a manufacturing process, which is very, very elaborate. If you don't get it right, then those sawtooth edges, razor sharp edges that I spoke about, will not necessarily be razor sharp. They will be rounded. It's a process that we follow, and our quality control is such that we remove drippers at frequent intervals, and we put them on a test bed, and we test the quality of that welding. We test that if a 1 litre drip an hour, if we say it is 1 litre an hour, it is 1 litre an hour. So that is constantly monitored and tested throughout our manufacturing processes.
Next question is, does water quality influence dripper efficiency or dripper turbulence?
Okay. Water quality is a vast subject. Water quality, there are three aspects to water quality. You've got physical, that's your solids, it's chemical, and biological. To discuss water quality issue with relation to drippers would take up reasonably another 3 of these webinars. So it's a subject that's pretty vast. But generally speaking, if you address the quality issues, put it this way, with water quality, many of the times you have to address it with filtration and with maintenance. Now, a poorly maintained drip irrigation system, just like a car, if you poorly maintain a car, you can have the best engine in the world, it's still not going to work well. The same with drippers. You can't do away with filtration, and you can't do away with maintaining. But basically, if you have a dripper that has the high turbulence coefficient and a better filtration area, the less will be the impact of bad quality. But it won't do away with it. You still need the proper filtration, and you still need your proper maintenance, and you still need proper investigation into the quality of your water, as I said, the physical, biological, and chemical aspects. And for that, you could get hold of our Netafim technical advisors, who will be able to assist you on your farm with your quality and its suitability, and what to do with it, how to use it.
Jerry, we also received a question from Abdul. What are the main advantages of using PC drippers, factoring the cost difference? Okay.
A PC dripper, whatever dripper pressure goes in, only one flow rate comes out. Now, a very skilled irrigation designer with certain conditions can get a very good design with a non-pressure compensating dripper. However, we use drippers that are pressure compensating when we've got long lines, and also when you've got undulating lines. Generally with those type of slopes, it's very, very difficult to design an irrigation system using pressure compensating drippers. And you've virtually got no choice. Whether you've got undulating, you can use pressure compensating, as you just mentioned, they are less expensive, but then you've got to put in more submains, okay, which means you've got higher PVC or polyethylene, whatever you make your submains out of. So you've got a higher cost of that. But a spin-off with pressure compensating drippers. Pressure compensating drippers have a diaphragm in them. That diaphragm, the nature of how that diaphragm works, does add in to the dripper a feature that expels and keeps drippers clean. So we will actually use PC. If you take greenhouses, we will, in greenhouses, very often they're on flat ground or just constant sloping ground, very often with short runs, only 30, 40 meters, sometimes less than that. There's no long runs. You don't theoretically need a pressure compensating dripper, but we put them in because they keep the drippers clean. That's one reason that we do it. There are other reasons that we use pressure compensating drippers in greenhouses. But basically, a pressure compensating dripper does act more efficiently at keeping a dripper clean than a non-pressure compensating, by virtue of the pressure compensating mechanism of that diaphragm.
Then there's also a question, are Netafim's drippers and drip line produced locally or imported?
I know there are people from outside Africa watching this. I'm speaking to you from Cape Town, southern tip of Africa at the moment. And I'm actually speaking to you from a factory. Outside these doors here is a factory where these dripper lines are produced for Africa, or Southern Africa, SADC. Netafim has factories throughout the world. It's good to have factories that are close to where you're going to use them. If you can imagine, particularly with heavy wall dripper lines, when you transport drippers, the heavy wall thickness is round, okay, and when you load that onto a container, you can't roll it flat, so you're transporting essentially fresh air. So the shorter you can use to the shorter distance to where you're going to use it, the less transport, the better. So strategically, Netafim has factories throughout the world in every region to give proximity to where the dripper lines are going to be used.
Thank you, Jerry. Then there's also a question, why is it worth paying more for Netafim drippers?
Okay. Yes, as I've just mentioned, what I've just shown you in the with the turbulence coefficient and the filtration area, as I just mentioned, that now determines the ability of that dripper to keep clean. With those factors, I've given you no sales yarn there. The turbulence coefficient, and I know there are engineers watching this, by the way. If you are an engineer, the turbulence coefficient comes from two formulas. It comes from what I was showing you just now, Darcy-Weisbach, and the turbulence part of it will be from Bernoulli's equation. We put those two together. So these figures just come from pure fluid mechanics that out of any fluid mechanic textbook. So these values that I've given you, if I just take the turbulence coefficient of in excess of 10 for our drippers, will have a higher value than our competitors, who, as I mentioned, was down in the 9. The coefficient was down in the 9, and likewise with the filtration area, and for that reason, to make a dripper to have those features, it costs more.
Then Jerry, there's also a question from France. He's asking, is it true that Uniram drippers start to deliver more when they get clogged? Why is this? And is this not a bad design which leads to a system losing pressure? Okay.
Depending, the Uniram dripper, if it should get clogged, it generally will start to lose less of a flow rate, but it can go to a higher flow rate. Essentially, if it does get to the stage where the dripper itself is getting clogged, it would suggest that possibly those aspects that I've just mentioned about now, your water quality, chemical, physical, and biological, have not necessarily been adequately addressed. There's no reason for any Netafim Uniram dripper, if it's going to go into an orchard, it's got to be last for 10 years. There's no reason that it shouldn't last 10 years, and that if that dripper is 1 litre an hour or 1.6 litres an hour, in 10 years' time it will remain 1 litre an hour and 1.6 litre an hour.